Okay. Hello, everybody. We are starting chapter 4 today, and we're going to start with section 4.1 here. This is being recorded in live lecture session. So I'll keep an eye on the chat here for those of you who are in the live session with me. If you got any questions at any point, just let me know. And yeah, for those of you watching on YouTube later, you can also ask questions. You'll just have to email me or come to office hours. So all good either way. So yeah, let's take a look at some section 4.1 here. In chapter 4, we're going to be looking at applications of the derivative. And to lay our groundwork here first, we're going to see how the derivative affects the behavior of a function, how it has an impact on the values of that function, how it can affect the graph of a function. And so that's what we're going to start by looking at here. We're going to look at extreme values of a function. And we got to start out with kind of a handful of definitions here to make sure we're all using the same terms. And a lot of these look very similar to each other. Like you can see the layout here of our definitions is really similar. So these are similar terms, but slightly different. Okay, so we are going to say that f of c, so this is a function value, value of f at some point c. This is the absolute maximum value of the function f if the following is true. If we can say that f of x is less than or equal to f of c for all the x's in f's domain. Okay, so what that's saying is that for all the x's in the domain, okay, so everything else, the function value at all those points, I have no idea what's going on with that highlighter there. That is pretty weird. But the function value f of x for all those x's in the domain is less than or equal to this f of c value. So f of c is like the big top of everything. That's why we're calling it the absolute maximum. Okay. So absolute maximum, that's like the biggest function value of everything. And then opposite to that, we have the absolute minimum value. Okay, so absolute minimum. And I am leaving a little space here in these definition blanks because there is another term that we can use for these. So I'm going to slip that in later. But for right now, we're just calling them absolute maximum, absolute minimum. All right, so f of c is the absolute minimum of the function f if basically the opposite of this is true. Okay, if f of x is greater than or equal to f of c for all the x's in f's domain. Okay, so here's like all the y values that go with the x values in your domain. All of those are greater than or equal to this f of c. So f of c is the littlest guy in this case. That makes it the absolute minimum for that function. Okay. So that's absolute maximum, absolute minimum. And then the next couple definitions do that type of thing, but on a smaller scale. So let's kind of look at what we're going to define next by using a picture here. Okay. So I'm just going to sketch out here some random function f of x. Okay. So there's x versus f of x. All right. And let's say our function has some sort of horizontal asymptote out towards the ends of its behavior. So maybe it kind of levels off through here. But then it starts doing some more interesting stuff for us. Okay, maybe something like this. Woo. All right. And then it levels off again. Okay. Let's say that's our function f of x, some random thing there. So we can see on this graph, you can probably pick out the absolute maximum and absolute minimum values because those are going to be the largest in the case of the maximum and the smallest y values on the whole function, okay? So if you look at our graph, your absolute maximum is going to be the highest up y value there. That's the largest value obtained by our function. So this is the absolute maximum. And when I label these, usually I tend to abbreviate them like abs for absolute. So abs max stands for absolute maximum. And then our absolute minimum would be the absolute lowest y value on the whole function. And that would be down here. We're assuming that it doesn't like go off to infinity in either direction, by the way. Get some sort of asymptote there. Okay, so that right there, that would be our absolute minimum, or abs min for short. Okay, but you might notice that there are some other like high and low values that are going on here. Like this y value right here, kind of at the top of that hill, so to say. That is not the absolute largest value on the graph. It's not our absolute maximum, but it is kind of a maximum in its own little sense, right? It's a high point on the graph. All right. It's just not the absolute highest. So that is something that we're going to call a local maximum. Okay, so this is a local max, and that's what our next set of definitions is going to be for. Okay, so we would say that f of c is a local maximum. Okay, of our function f if we take the same idea from like maximums. Okay, your f of x values in general are less than or equal to this local maximum f of c value. This is only though when x is near c. Okay, when x is near C. So this is not for all x's in the domain anymore. It's just in kind of some little neighborhood around the C value. So like if this is our local max f of C, this would be the value C down there. And so the local max is like, okay, it's the biggest thing when x is near C, you know, like within some little interval on the x-axis there. It's the highest y value associated with those x values. Okay, so that would be a local maximum. Oops, ditched my y-axis there. There we go. So we've got a local maximum, and then we're going to define a local minimum to go with that. Local minimum Okay, so f of c is going to be a local minimum of our function f if the other y values, so the f of x's, are greater than or equal to that f of c guy. So this is the little guy here in its own little area. So when x is near c again. All right. So you can kind of see some structure similarities here between the absolutes and the locals. If something is a maximum, we have this part in the definition, okay? F of x is less than or equal to f of c, because to be a maximum value, f of c needs to be bigger than the things around it, okay? So that hits maximum. And then to contrast with that, if you see minimum, we have this type of definition, okay? So the other f of x's have to be greater than or equal to f of c in order to make f of c the minimum value. All right. So there's the difference between maximum and minimum definition-wise. And then absolute is for all the x's in the domain versus local. Okay, and so those local maximum, local minimum, those are only when x is near c. Okay, so as far as like the absolute and local thing goes, you can think of it kind of like local in the sense of like your own little local area on a map. Like if something's a local maximum, let's say, we're saying that it's the biggest thing in its little neighborhood, all right? When x is close to c, this is the biggest thing we've got. Might not be the biggest thing on the whole graph, but in its little local area, this is the big guy. So that kind of leads us to our other term for absolute maximum or absolute minimum. These are also called global maximums or minimums. Okay, so absolute maximum is the same thing as a global maximum. Or absolute minimum, you could also call that a global minimum. Oops, if I can write it correctly. There we go, global minimum. Okay, because yeah, that really kind of emphasizes the difference between a local and global. Local is just in the little neighborhood. Global is for everything, like on the whole planet that is this function, if you want to think of it that way. So all the x's in the domain, that's like the whole world of this function f. So that's why we can call those global maximums and minimums. And then the other term for local is not quite as exciting in my opinion. A local maximum can also be called a relative maximum. All right, and a local minimum can also be called a relative minimum. Okay, and the kind of thought process behind those terms is that we're looking at values relative to what is around them. Okay, so relative to the things around it when x is near c, okay, we would say this is a relative maximum if it's the highest y value relative to the other y values in that area. All right. As opposed to being like an absolute maximum where it's not just relative to the things in its area, it is the absolute biggest thing for all of the x's. This is the biggest y value. So absolute, it's like everything, versus relative, which is just relative to the things around it. Okay. So that's absolute and relative, and then we've got global versus local. So these are all terms that you might see pop up at different times. So that's why it's just good to know all these different names for them. Then we got one more name to look at here. Collectively, all of these terms together, all four of these, absolute maximum, absolute minimum, local maximum, local minimum, these are all referred to as extreme values. Okay, that's the title of this section. Ta-da! Extreme values. Because they are the extremes here. They're the biggest or the smallest, either on the whole graph or in their own little area. So these are the extremes of our function behavior. Those can also be referred to as extrema, which is, I think that's a play on the, maybe it's a Latin root there. This is the plural version of the word extremum, extremum, which would be just one of those extreme values. Like an absolute max is an extremum, but when you look at more than one of them, you call it extrema, plural. Okay, speaking of extrema, let's label our other ones on this funny function here. We got our local max labeled right there. We got our absolute maximum for the whole function up top there. Absolute minimum, lowest thing on the whole function down there. And then a couple other ones right down here, kind of at the bottom of that valley of the function. What would that be, do you guys think? For those of you on the live session, what does that look like? Of those four labels. Give you a sec to put it in the chat if you would like. Hint, we have another one of them over here. This is going to get labeled with the same type of thing. So what do we think? Yeah, cool. I got two answers in the private chat and you are both right. So one person said relative minimum and the other person said local minimum, and those are both referring to the same thing. And you're both right. Awesome. So yeah, those are relative or local minimums or minima. I think our book tends to use the local term for it. So I'll label them as local, but just know that if you said relative, you were also correct. So local minimum, local or relative minimum there. All right, nice. Let's see. I guess that does give us another kind of thing to note here. You can have more than one local minimum. You can see we've got two of them right there. You can't have more than one absolute maximum or minimum because that's for the entire function, or at least for an interval of a function, as we'll see later on today. But yeah, you can have more than one of the local types. And actually, someone just messaged me asking, isn't there one more local max? And yes, there is. That would be right here, kind of at the top of that hill. That would also be a local maximum. So good looking out there. Local max, yeah. So maximums in general kind of look like they are at the top of the hill. Local would be like kind of the smaller hills in their own little area. That's the top there. Absolute would be the big top of the hill. All right, so top of the hill makes a maximum. Bottom of a valley is where a minimum is going to be. So minimum, minimum, minimum. So there's all of our extrema, it looks like. There is one more point that I would consider kind of questionable on this graph. Right here, I'm not really sure whether that would be a maximum or minimum or anything worth looking at, just because my drawing was not fantastic. If it bumped up a little bit more, then yeah, that would sure be a maximum, like a little local max there. But the way I drew it, it doesn't particularly look like it. So we'll just leave that one alone. We've got our main points labeled here. Okay, so there's our extreme values. I'll stop the recording here and then we'll pick up in the next one.